The machining error of the blank is quite large at around 200 micrometer. It is thought that the weak connection of the rib. Now let's have a look at the abutment machined by both methods and discuss the causes of error and solutions. We can see that both machining methods have an error of about 20 to 30 micrometer. This is good enough for clinical use. Let's zoom in on the connection error. We can see that the CNC machining error is over 50 micrometer. A blank is called a premill. It seems to strongly imply that the connection and screw hole are pre-machined. This is why the connections are more precisely machined than with the CNC. This is often the first reason for preferring a premill. Let's leave the connections out and just align the upper part for comparison. The concave in the chamfer margin, indicated by the red arrow, must be designed considering the size of the machining tool. The shape error indicated by the black arrow is common in blank machining. This is caused by under-machining the concave side of the abutment. In CNC machining, the orange area is an error caused by manually removing the little bit left after the connection is removed. Proper setting of the tool can reduce errors. Typically, the thinnest tool for processing custom abutment is 1.5 mm in diameter. Setting it to 1.7 mm with about 15% allowance can avoid the problem of under-machining. Abutment design with blank machining is not good for concave areas. In particular, retention groove is not recommended not only because they are not machined accurately, but also because the inside of the zirconia crown is not machined properly. These offsets are common in blank machining results. It's a problem caused by the misalignment of coordinates when machining upside down, and it must be solved by calibrating the machine. If you're using a jig to machine multiple blanks simultaneously, you will need to measure the position of each blank to resolve the error. Here we will show the error that causes the abutment to bend sideways relative to the connection during machining. The machining error of the blank is quite large at around 200 micrometer. It is thought that the weak connection of the reverse jig is deformed due to significant lateral pressure during roughing. To reduce this machining error, it is helpful to reduce the machining speed and manage the removal efficiency of the tool. It is also important to keep the usage period of the reverse jig that holds the blank so that the connections do not become loose. CNC machining error is relatively small at around 50 micrometer, but there is still a one-sided error. My opinion on this issue is that the CNC machining of the connection is not precise enough. Here's an example. On the left is the design file, and on the right is the scan data of patient intraoral connection. Let's align the two files based on the remaining teeth and compare the difference between the design and the machined abutment. This way, we can see the error in the machining of the abutment. The cross-section shows a lateral error of about 200 micrometer. It would be good to refer to the machining video while listening. The blank is positioned like this and machines start sideways. If the machining speed is fast or the machining efficiency of the tool decreases, the lateral pressure on the blank increases and may be pushed to the opposite side. This can happen more easily with a reverse jig due to the weak connection. To maintain removal efficiency, you need to maintain the blade of your machining tool. I was able to observe the damaged connection on the reverse jig used on the microscope. Reverse jigs also need to be maintained properly. From here, we are going to compare the tolerance of the different models we used to correct machining errors. The first is the reference model. For the reference model, we created a plaster model containing 5 implant lab analogs. Then, we scanned it with Medit table scanner. The second is an intraoral scan. The reference model was also scanned with a Medit intraoral scanner. We compared the table scanner and intraoral scanner scan results. The error range is within 100 micrometer on both posterior molars and around 50 micrometer for the scan bodies. The third is a replica plaster model. To reduce the error of plaster model making as much as possible, a second model was made by reusing the impression with which the reference model was made. This is comparison of the reference model and the replica model. Errors are rarely found in this part. However, errors in the scan body shows a range of 60 to 100 micrometer, which is larger than that of the intraoral scan. The source of this error is thought to be the accumulation of connect error between the lab analog and the impression cupping when creating the platter model. The final model is a 3D printing model. When creating a 3D printing model, there are many factors that can cause errors. As a side note, I had a researcher in my lab who specialized in 3D printing only. When looking at the result, it would be helpful to understand that the results are more controlled than typical 3D printing results. We connected lab analogs dedicated for the 3D printing model and scanned it. You can see that the 3D printing model itself has a very large error. The error of the scan body does not exceed 100 micrometer vertically, but it seems to exceed 200 micrometer laterally. Let's look at the overall comparison. The intraoral scan has a slight scan error, but shows the lowest level of scan body error, as there is only the error of connecting the scan body once. For the plaster model, we used the same impression to reduce the error of the impression, so the plaster model itself had the lowest error. But as a result of the additional error introduced by the new connection, the scan body connection error exceeded 100 micrometer. The 3D printing model was found to be clinically unusable due to the error in the model itself and the large connection error with the lab analog. Summarizing the above result, we can conclude that a model-free compensation method would be the best way to go.